we, coming back to consolidate this for the left bound, um, each one of those widths were 1. So we could factor out a 1. And then factoring out that 1, now let's, f of 0, let's evaluate it. Well, our function is sine of x plus 2. So we have sine of 0 plus 2, and then we have f of 1 plus sine of 1 plus 2. So that's f of 0, f of 1 plus f of 2 plus sine of 2 plus 2 plus f of 3 sine of 3 plus 2, and then plus f of 4 sine of 4 plus 2. We've got 1, 2, 3, 4, 5 plus 2's. So we could simplify this even further. Our left bound would be 1 times. We've got 5 plus 2, so that's 10 plus sine of 0 plus sine of 1 plus sine of 2 plus sine of 3 plus sine of 4. And that would be my left bound approximation. Let me just jump over to the right and then we'll go back to the mid. To do the right bound, same idea. We're going from 0 to 5. We're using our right bound. So in this first interval from 0 to 1, I'm going to use my right bound to get a rectangle to approximate that area. So it has a length of 1 and a height of f of 1. Plus, in next interval from 1 to 2, I'm using my right bound, and that has a width of 1 and a height of f of 2. Plus, now from 2 to 3, I'm using my right bound, 1, my width, times my height, f of 3, plus right bound, I've got width of 1 times f of 4, and then my last rectangle has, again, a width of 1 and a height of f of 5. So notice for these heights, I'm choosing my right bounded limit, or sorry, my right bounded value. And if we were to simplify that, let's extend the page. If I were to simplify that for my right bounded, again, all of them have a width of 1, so I could extract a 1, factor out a 1, and then f of 1, so I've got sine of 1 plus 2, that's f of 1, plus sine of 2 plus 2, plus sine of 3 plus 2, plus sine of 4 plus 2, plus sine of 5 plus 2. So simplifying that, we've got the plus 2 showing up just in the same way. So we've got a width of 1 times 10 plus sine of 1 plus sine of 2 plus sine of 3 plus sine of 4 plus sine of 5. Very similar to my left bound. The only difference is that my right bound has a sine of 5 and my left bound has a sine of 0, and otherwise they're identical. Last case, how do we find the midpoint approximation? Well, same sort of thing between, from 1 to 5. We have 5 intervals, and in each interval, we're going to choose the midpoint to get my y height, or to get my height, my y value, which is my height. So in that first rectangle, it has a base of 1, and we're using the midpoint between those, so f of 0.5 to get my height, plus 1 times, so use the midpoint there. So 1 times f of 1.5 plus 1 times f of, so in my next triangle, using the midpoint, it's f of 2.5 plus 1 times, in my next rectangle, it's going to be f of 3.5. And in my last one, to get the area approximation, it's 1 times f of 4.5. So for my midpoint, it's going to be very similar once again. You know, if I try to uh, write this in a nice way for my midpoint, once again, they all have a width of 1, and you're always going to have the same width, so you can always extract your width outside, factor it out. And then, you know, f of 0.5, well, when I do f of 0.5 plus f of 1.5, f of 2.5, once again, same as before, same as the other ones. I'm going to get this 10 out in front. So I'm going to get 10 plus sine of 0.5 plus sine of 1.5 plus sine of 2.5 plus sine of 3.5 plus sine of 4.5. And notice the idea is we've got 3 different ways of approximating the area. The left bound is when I choose in any given interval, I'm choosing the left y value. My right bound, I'm choosing the right y value. And my midpoint, I'm choosing the middle y value. And there's just 3 different methods for getting the area. And you could imagine that probably the best way to approximate the area would then be to average these. So let's look at one more example, and then we're going to develop a calculator computer program that can do this quickly for us. So what we want to do is, given the function ln x, we want to approximate the area underneath the curve from 1 to 5. So we're going to do 2 approximations, one a left bound and one a right bound, or left hand and right hand. So you know that ln x looks something like this, where it has the x-intercept at 1, and we're going to go up to 5. And so let's see, 2, 3, 4, 5. And in our first, if we're looking at a left hand approximation for the area, so in our first interval from 1 to 2, which has a distance, you know, a width of 1, I'm going to use my left bound value to get my first area. So 1 times ln of 1. And then from 2 to 3, I'm using my left bound, so plus 1 times ln of 2. And then from 3 to 4, I'm using my left bound value plus 1 times ln of 3. And then for my last, from 4 to 5, I'm using my left, so plus 1 times ln of 4. So that's an approximation. That's a left hand approximation for the area underneath the graph ln x between, for the x values 1 to 5, using 4 intervals. What about a right-handed? Well, it's going to look very similar, only now in my right-handed, so 2, 3, 4, 5. In my right-handed, in my first area approximation, I'm using my right value. So width of 1 times ln of 2 plus, and then from 2 to 3, I use my right bound. So plus 1 times ln of 3. And then from 3 to 4, I use my right bound again. So always using the right-handed. So plus 1 times ln of 4. And then for my last rectangle between 4 and 5, again, using my right-handed value. So it's going to be 1 times ln of 5. So this here is my right-handed sum, versus up here, which is my left-handed sum. And notice that there's a lot of similarities. We've got the 1 ln 2, 1 ln 2, 1 ln 3, 1 ln 3, 1 ln 4, 1 ln 4. So this is a way for us to start thinking about how do we find area underneath a curve. Okay, well it can be a tedious process, and you can imagine the way to get this more accurate, the more and more accurate, would be to let n approach infinity. As n approaches infinity, our delta x approaches 0. So we're looking at much smaller intervals, and this would improve our accuracy. But while improving our accuracy, it also would hugely improve or increase our, make it much more time consuming. We'd have to do a lot more multiplications. So we're going to create a program right now that can do this work for us instantaneously. We're going to have to put in a little bit of effort to make the calculator program, but once we make the calculator program, it can almost instantaneously generate these approximations for us. So let's do that now. So this only works for 83s and 84s. If you don't have one, sorry, I don't know what else to say. But this program, it's only going to work for TI 83 and 84. There may be comparable ones for the Inspire or 89s or other types of calculators, but this is the one that I know. So follow along with me. We might have to start another video halfway along, but let's get started. So you've got your calculator, and what we're going to do is create a program. So go to Program, press Program, and we're going to make a new program. And the new program that we're going to make is called rsum. So it's already in alpha, so you can go just press R S U M, press enter, and now we're starting to program. And I'm going to give you this program and work through it with you, but I'm going to suggest that there's going to be a lot of opportunities for you to create your own programs, and I highly encourage you to program anything and everything that you can. It's a great skill. So what we want to do is input our left bound. So for example, in the last problem, our left bound would have been 1. So we want to input our left bound into our calculator. And the way we do that is input. So press Program and go up here to the right for input output, and there's our input command. So press enter, and we need to put parentheses. So we have to press alpha parentheses, and then we're going to do left. So I think it's helpful to do an alpha lock. So press second alpha, and we're going to spell out left. So LEFT. And they have a colon there. I don't think we really need to do that. So put the parentheses, get out of alpha, and then put comma, and then we're going to put alpha A. And so that means that we're storing our left bound in A. That's what the programming language is saying. And then we want to input our right bound. So we're going to go Program, go to Input Output, go down to Input, and let's do second alpha lock again, parentheses, and we're putting right. So you should be doing this along with me. Once you get this stored into your calculator, it's there for good. And get out of alpha, comma, and we're storing our right bound into B. The next command is sort of a weird command, and this is where we're going to tell our calculator whether we want to do left bound, right bound, or midpoint. And it's sort of an interesting name. We're going to call it X choice. But I'm going to stop the video here, and we'll finish doing this program in the last video.